Alright, hello and welcome. Today's Monday, March 23rd. We're going to continue with our circuits unit. We are almost at the finish line as far as content is concerned. We'll finish off circuits and then we just start reviewing for final for the AP test that is coming. I hope you've heard of all the announcements. Mr. Hussey should have sent out an email. I think you guys all got it. Basically, we have 2 more weeks of online school, and then after these next 2 weeks is our spring break. And currently, school is scheduled to come back or to be in session again in 3 weeks after our spring break. So 2 more weeks of online, 1 week of spring break. Now we call it a spring break. It's not really a break because you're AP students. You don't get a break until after the AP test. So during spring break, you do your spring break homework. Make sure you check the AP review section under Unit 8. You'll see another link, AP review. And then there's spring break homework, the 2 practice tests I was talking about. So that's that. Oh, we have a new follower, Emma. Welcome, Emma. LEOC announced through May 1st. Do you know if ALCO will follow? Potentially, but currently it is until after spring break. Now the College Board hasn't told us when the online test will be, etc. But we will follow College Board as much as we can. It is possible that we'll have to cancel some of our post-AP projects, but I don't know that until I actually get some dates. We might be able to keep the bottle rocket project, but we'll do one of them at least so that we have enough points in the test category. Otherwise this test category will just be whatever your final is, which is not good, right? We want more points in the test category. Alright, so that's that. Today we're going to talk about Kirchhoff loop rules, and then I'll set you off with the next activity for Unit 8, and that's the advanced circuits. I've opened up the next Mastering Physics, which is the Chapter 23 homework, due next week. Check the calendar on Mastering Physics. Alright, number 1, Junction Rule. I guess it's called Kirchhoff's loop rules. First one is Junction Rule. We're just going to do 2 of them today. Junction Rule, and that's just current into a junction equals current out of junction. Okay. Recall that in any point where you have a splitting off of wires going in different directions. Now sometimes you get questions like abstract or conceptual questions where instead of drawing a circuit, they're just drawing arrows. And so the arrows indicate the direction of current I. So you might have arrow this way, like so. So if they say that this is 2 amps going in, and this is 0.5 going upwards, that means whatever's left over must be going to the right. Okay, so whatever goes in must equal whatever comes out. Simple as that. Number 2 is, hey, Mr. Z. Hey, hi. 8 and. I don't know who you are, but welcome. 8 and. So the next one, what's called a loop rule, which is a bit more important. Oh, it's Aiden Garospi. Welcome, welcome. Loop rule, which is the sum of all voltages, or sum of all voltages around a closed pathway equals 0. This is very interesting in that as you go around a circuit from one circuit element to the next, some circuit element may give you a voltage, some circuit elements or other circuit elements may take away your voltage. Essentially, as you go plus and minus all the way around a closed loop, you end up with 0 volts. Okay. Typically, batteries add your voltage, give plus V if going from the negative side to the positive side. Recall that the battery symbol is a small line, big line. So if your pathway sets you off so that the direction of your path is going from left to right, such that you are forced to go from the negative side into the positive side this way, then this will add voltage. Okay? But if your pathway is in the opposite direction to the battery, so if your battery is oriented the other way, like so, but you're trying to go to the right still, and we'll talk about pathways in a second. But anyway, if you're going from the positive side to the minus side, you're going to subtract the voltage of the battery. All right. And of course, resistors. There is an easier way to look at it. It would be if the direction of the current flow matches the direction of the pathway. Resistors drop voltage, which is another way of saying subtract V. When the pathway is in the same direction as the current. Okay. And if your pathway is in the opposite direction of the current, then a resistor would actually add the voltage. Okay. These are the two ways that you would show work in a circuit analysis or circuit FRQ. If there was a circuit FRQ on your final, it's probably not going to be on the AP test, but on your final, it potentially could be. But this is how you would show your work by writing down the loop rules and the junction rules. It's basically linear algebra stuff, so if you like algebra, stay tuned. Let's see, let's draw a simple circuit. Here we go. No, let's just do 3. Should we do 4? I guess we can do 4. Undo. Ooh, this looks different. Let's call this R1, R2, R3, R4, R5. Of course, we should be able to simplify our circuits by identifying which ones are series, which ones are parallel. You can see how when the current goes through number 2, it has to go through number 3. Therefore, 2 and 3 are series. Same thing with 4 and... oh, I have 2 4s. That's not good. This is 5. Whatever current goes through number 4 will also have to go through number 5. Therefore, 4 and 5 are in series. Okay. So one way to do it is to simplify the circuits. And so we can write R1 here. And then we have R23. And notice how after R23 it connects to the bottom of the battery, like so. Make sure we have one big line, one small line. There we go. And the next one from this junction, it also connects to the bottom of the battery. So the next one is parallel to 2, 3, and that's R4, 5. Stovetop. Stovetop, are you Posty? Ryan Posty? I'm just going to take a wild guess. If I'm right, let me know in chat. Ah, dang it. I was so sure you were Ryan Posty. Period 2. Who would... Evan? Are you Evan? No? I don't know. Alright, so now we can see how 2, 3, 4, 5 are close. Must be Ryan K. How is that close? Exactly, like, how am I supposed to know you're close to Evan? Who looks like Evan, talks like Evan, but is not Evan? Must be Ryan K or something. Alright, so R23 and R45 are parallel, and then it's in series with number 1. Okay, so the rec equation, the formula, would be R1 plus R2 plus R3 parallel to R4 plus R5. Okay, so you gotta do the series first, put them together, then do the parallel, and then another series with R1. Okay, so instead of doing all that, one way to do it is to write loop rules. Let's call this V. First, go ahead and use basically just the logical flow of current from the positive end to the negative end to establish the direction of current through each resistor. You can basically guess, but you want to guess with reason. And it's okay to be wrong in choosing the direction of current, because when you do the algebra, you might get a negative number. That negative current will just tell you that the direction that you chose for your current originally is actually wrong. It's in the other way. It's the opposite way. But anyway, some of the circuits you can actually just guess easily, in that we know that current will come out of the positive side of the battery. Therefore, I1 would be pointed to the right across resistor 1. And then we get to this junction here, and at this junction it splits off into 2 different directions. Some of the current will go through here. This is I2. And then the rest of the current will go through here, I4. Okay. And it will continue onwards. This is I3. This is I5. Oops. There's some foreshadowing there. I5. And then finally we're back out. Now, on the side of the battery, if you have I1 coming out this way, that I1 is the same I1 that went through resistor 1. Okay? If you have I1 coming out, that means you have to have I1 going in. What comes out must equal what comes in, etc. The junction rule. Okay, let's go and do all the junction rule stuff. We know that at this junction, we have I1 to the right, downwards is I2, and then we have I4. I4 to the right, I2 down, and I1 to the right going into the junction, the other two coming out of the junction. Alright, so our junction rule gives us I1 is equal to I2 plus I4. Okay, and based on the fact that some of these are series, we can kind of simplify our currents. We don't have to use that many variables. Basically, I2 is equal to I3, so we can replace I3 with a bunch of I2s. And then we also know that I4 is equal to I5, so we can replace all the I5s with I4. Okay, so we have less variables to deal with. Okay, next up, we set up pathways. Pathways go from the positive side of the battery and form a closed loop to the bottom side of the battery. Whichever battery you come out of, you have to go back into that same battery for a closed pathway. Okay, this technique will allow us to do circuits with 2 batteries or 3 batteries. If you want to learn more, consider majoring in electrical engineering. But let's go and do a pathway. Continue. We'll use pathway green. Pathway green is out of the battery, through resistor 1, through the first route, and then back in. Okay. Alright, so that's pathway number 1. And we want to write the loop rule for this. Okay. Voltage around a closed pathway is equal to 0. That's our equation. We'll go ahead and start with the battery. Notice how we're starting from the positive end, and then we go through. So we're going from negative into positive. We're not going in the opposite direction. We're going through the correct direction in that from bottom side to the top, we're using it as an elevator. And so we do V, which is the battery. Let's just call it. Sometimes you might see this epsilon instead of V. So if you do, use epsilon. Use whatever variable the College Board gives you. EMF. V, and then now we go through the loop. The first element we encounter is R1. Okay? And our pathway is in the same direction as the current that we have established arbitrarily. Since it's in the same direction, that resistor, by going through it, will decrease our potential by V1 amount. So we're going to subtract V1 from our equation. When I go through resistor 2, I will lose V2, so minus V2. When I go through resistor 3, I will lose V3, so minus V3. And after going through resistor 3, we are now at the bottom side of the battery. Therefore, we're done with our pathway. We're going to set that equal to 0. Okay. And you don't have to leave it in this form because it's not very useful in this form. Let's go and plug in the actual Ohm's law for each encounter. Starting with our battery, we have V. V1 is equal to I1 times R1. V2 is I2R2. Okay. V3 is I3R3, but I3 is the same as I2. Therefore, I can say that it's I2R3. And it's equal to 0. Okay. Our next one, let's go and draw another pathway. I'll use blue. This next pathway, start with the battery through R1. Notice how both pathways have to take R1. There's no other path. But at this fork, we're going to continue moving forward to the right instead of going downwards. We'll go through R4 and then 5, and now we're at our destination, the bottom side of the battery. This is path 2. Okay. For path 2, chat, go ahead and try this on your own. Go and write down the equation, starting with the battery as you go around the loop. For path 2, what is the equation? All right, well, very good, I guess. We have everyone sleeping. V minus V1 minus V4 minus V5 equals 0. Good job, V-Boo. So this would be V minus I1 R1. It's the same voltage drop. Minus I4 R4 minus, now the current in resistor 5 is the same current that goes through resistor 4. Okay, whatever went through 4 has to go through 5 because there's no other pathway to split off. So just go and write I4 R5. All right, so we have really nice, two equations. We also have the junction rule. That's our third equation, and this will allow, these three sets of equations will allow us to solve for all of the values, given. Typically, you're given capital V, the battery, and all the resistors, Rn, where n goes from, oops, I should write, I usually use this notation when I do this, from 1 to 5. Whoa, no, that's not really a correct notation, I just made that up. But you'll definitely see that notation next year in AP Physics C. Okay, so given the resistors, you should be able to find V1, V2, I'm just going to do dot, 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 V5, and you should be able to find I1 through I5. Okay. You'd have to, you'd basically get a bunch of linear algebra equations. You do substitution method, solve for one variable, plug it into another equation, solve for that variable, plug it into another equation. It's like instead of having just 2 sets of linear equations, you would have 3. We could try it, I guess. Let's see. Let's just make it easy. Let R equal 10 ohms for all, and V equals 10 volts. Alright, this would be an easy way. Let's see. So equation 1, let's use green. So the first equation would be 10 volts minus, and it's okay to drop the unit for now. It'll just be a linear algebra equation. I1 times R1. R1 is 10, so 10 I1 minus 10 I2 minus 10 I3 oops, 10 I2, sorry, 10 I2 again, equals 0. So that's the green equation. We can simplify this. We get 10 minus 10 I1 minus 20 I2 equals 0. Okay. This will allow us to solve for I1. We get 10 minus 20 I2 all over 10 equals I1. Divide by 10, this gives us 1 minus 2 I2 equals I1. Alright, starting with blue now. Blue is V minus I1 R1 minus I4 R4 minus I4 R5. So that's 10 minus 10 I1 minus 10 I4 minus 10 I4 equals 0. Okay, go and simplify. So that's 10 minus 10 I1. Well, all the 10's gonna turn into 1, so that's nice. Okay, let's just solve for I4 here. I get 10 minus 10 I1 over 20 equals I4. Simplifying it down, which gives us 1/2 minus 1/2 I1 equals I4. Okay, we already know what I1 is. I1 is 1 minus 2I2, etc. Oh, did I miss any other junction rule? I may have missed a junction rule. Uh-oh. Oh, 1 plus I1 is equal to 2 plus 4. Okay. I can substitute in I1, or I can use the junction rule. I1 is equal, so I have two things to do here. I have these two, of course, but I also have the junction rule. I1 equals to I2 plus I4, that way. Okay. And you can always try to create more junction rules by looking at points. For example, if you try to look through here, but sometimes you'll see that you get the same equation twice or thrice. You have I1 For example, at this junction, you have I1 going out of the junction, and I3, which is I2, I2 going in, and you have I5, which is I4, I4 going in. So 2 plus 4 equals 1, or I2 plus I4 equals 1, which gives us the same formula that we got. All right, chat, what's our next step? How do I use the junction rule equation to solve for one of the variables? Substitute for I1. Oh, okay. Substitute. Bubble guy, do you want to substitute I1 into I4, or do you want to substitute I2 into the I1 equation? You could do that. Okay, I don't know what you want, but let's go and do that. So I1 minus I4 equals I2. Sure. Very good. So 1 minus 2 times I1 minus I4 equals I1. Okay, so we're going to substitute this into here. I1 minus I2 minus 2 times I1 minus I4 equals I2. Okay, let's go and simplify this. So we get 1 minus 2I1 plus 2I4 equals I1. Alright, let's go and isolate I1. So add 2 I1s to both sides. This gives us 1 plus 2 I4 is equal to 3 I1. Okay, go and divide, and then finally we have 1/3 plus 2/3 I4 equals I1. Now we can substitute. This into here. This gives us 1/2 minus 1/2 times 1/3 plus 2/3 I4 equals I4. Yeah. It looks very messy. It's the first one that's the hardest. Once you solve for one of the variables, the rest are really easy because you can just substitute that back into the other formulas, and the dominoes just start falling and everything becomes easier and easier. So it's the first variable that's the hardest to solve for, but after that it's really simple. Let's see, what do we get? 1/2 minus 1/2 times 1/3 is 1/6 minus 2/6 I4 equals I4. Okay, go and add 2/6 to both sides. We get 1/2 minus a 6th. This is same as 3/6. So 3/6 minus 1/6 is 2/6, which is 1/3. 1/3. And then here we're going to add 1/3 to 1, which is 4/3. 1/3 plus 1 is 4/3. And finally, go and multiply by the reciprocal. The 3's cancel, giving you I4 is equal to, it's 3/4. The 3's cancel, 1/4. So 0.25 amps. Okay. Once you solve for I4, then you can plug it back into here, solve for I1. So 1/3 plus 2/3 of 0.25 gives you I1. and so on and so forth, and you just crunch out all the i's. Once you have all the i's, then you can do all the v's, where v1 is equal to I1 R1, v2 is equal to I2 R2, etc. Okay, so as soon as the first domino falls, the rest are pretty simple. Is there another way to solve this? Yes, by simplification. So when we simplify down, we can solve for it. Once you know what rec is, you can solve for I total, and you can see how I total is equal to I1. So alternative approach, alternative solution. We know that rec is equal to R1 plus the parallel of 2, 3, and 4, 5. This is 10 plus 20 parallel 20, right? So that's 10 plus 10 is 20, 10 plus 10 is 20, 20 parallel 20 over rec for 2, product over sum. When you have the same resistors, product over sum will just give you half the resistance. So that's 10. And so rec is 20. Which means I total is V total over rec, which gives us 10 volts over 20 volts. I think we're going to leave the we're going to have to leave the activity thing. You can get started, of course. Leave the activity thing for tomorrow. Well, 20 volts, that's not right. Rec is 20 ohms. 20 ohms. And this gives us half an amp. Great. Okay. From there, then you have to analyze the circuit. You'll see that all of the current goes through resistor 1, so I1 is equal to I total. So you can say I1 is equal to 0.5 amps. Once you know that, you can find V1. V1 should be 1 I1 R1, which is half times 10, which is 5 volts. Okay. So once you lose 5 volts, then whatever is left at 2 and 3. So if we have 5 volts remaining to pass on to resistor 2 and resistor 3. Same thing, 5 volts remaining to pass on to 4 and 5. Remember, you can only choose one pathway at a time, so you can only do this one set at a time. So this 5 volts that's remaining has to be split up between 2 and 3 to 2.5 and 2.5. V2 plus V3 equals 5 volts. Therefore, V2 equals V3 equals 2.5. Okay. If you have resistors in series and they're both the same resistance, they will drop equal voltages because they have the same current. And if you only have 5 to spare, then they both will drop 2.5 and 2.5. Okay. Same thing with 4 and 5. Right. Okay. Of course, these are things that you can do if you can look for patterns. Otherwise, you're going to use Kirchhoff's loop rules because that allows you to solve for any combination. So if your resistors and stuff are not like perfectly divisible, like 10s and 4s and 2s, and you have like random numbers like 56, 42, then yeah, you're going to have to stick to the linear algebra stuff. Alright, so let's go and verify. We know that I4 should equal V equals IR, so V divided by resistance. Notice how we get 2.4 volts divided by 10, and this gives us 0.25 amps. Yay, that's exactly what we found when we solved it using linear algebra. Alright, so the method works. Now, why is the method useful? Well, it's useful when you have more complex circuits that you cannot simplify. So let's take a look at a different circuit with 2 batteries. Whoa. Okay, let's call this epsilon 1 and epsilon 2. This is R1, R2, R3. Okay. Let's go and draw some current directions. I'm going to say that the current goes through this way, down this way, and to the left this way. Why did I choose these? Remember, it's kind of random. You can definitely choose the other way, and that's okay. Okay, but you want to use as much logic as possible. Notice how we have the positive end here, positive end here. It's almost like turning on 2 faucets at the same time. When you turn on 2 faucets at the same time, the water will gush out of both ends and then kind of meet at this junction here and then funnel through downwards. So that's why I chose it this way. Now again, you could choose it the other way, and your equation will just give you negative current. That negative current tells you that the current is actually the same magnitude but in the opposite direction. Okay, let's go and do our pathways. I can do 3 different pathways just to show you that I can, mostly. We'll start here, go through resistor 1. Go through resistor 2, and then go to the bottom of the battery. That's pathway number 1. There's also another pathway. Let's go and use blue. And that is starting from E2 now instead, going through resistor 3, going through resistor 2, and then going to the bottom of E2. And I'll do a third one. You can also figure out there's a 4th one, but I'll let you figure that one out on your own. Well, here's the third one, starting from E1, going through resistor 1 again, because there's no other choice. But let's go and skip R2, but go the opposite direction. Whoa, whoa, going into the battery, and then back. So the outer loop. Okay, so these are pathways. The pathways. So let's go and write down the equations for each pathway, starting with orange. Pathway 1. Pathway 1, we have epsilon 1 minus, notice how it's minus V1 because it's the same direction as the current. Let me go write that down. This is I1, this is I2, this is I3. So epsilon 1 minus, I'm going to shortcut, go straight to the equations. This is I1 R1 minus I2 R2. And once we pass R2, we're finished. We're at the bottom of the battery. Our loop is complete. It's going to equal 0. Let's go and do the blue path. Okay. For the blue path, we're starting from the second battery. So it's epsilon 2. Epsilon 2. And notice how blue path goes in the same direction as the current that I've identified. So that means that we're going to subtract I3 R3. And then we'll subtract I2 R2, and it also equals 0. We're done with our loop, so it must equal 0. All right, now for the more complicated green loop. Okay. We'll start with our first battery, epsilon 1. Okay. From there, we're going in the same direction as the current for resistor 1, so subtract I1 R1. All right, this is where it gets interesting. My path takes me to the right, The flow of current is to the left in the opposite direction. So what do I do? Yes, VBoo, you add. Very good. So we're going to add, oops, green, there we go. We're going to add I3, R3. I3 add R3. Okay. All right, we're going to keep going. Keep going. Now you're going into the battery the opposite way. Whoa. We're going from the positive side into the negative side. What do we do with the battery? It looks like we're doing the opposite. Minus epsilon 2. So we're going to subtract the battery because we're going in the opposite direction. All right, are we done? Yes, it looks like we're done. We're at the bottom of our battery, so we are done. Okay. All right. But always add on the junction rule. Don't just do the loop rules. That's not enough. Always write down the junction rule. So let's do a junction rule. Any critical points that you might notice. I would say this is a critical point right here. Okay, what is happening at this junction? Well, we have I1 going into the junction. We also have I3 going into the junction. It goes into the circle, into the dot. But we have I2 coming out of the junction. All right, chat, go ahead and write down the junction equation based on this diagram here. Remember, it's current into the junction equals current out of the junction. There we go. So I1 plus I3 must equal I2. Okay. So using all of these equations, you should be able to solve for any of the variables, right? Now, you don't technically need 4 sets of equations. Remember the rule for linear algebra in that if you have 2 variables, you need only 2 separate equations that are not reliant on each other, independent of each other. So if you have 3 variables, unknown variables being, notice how I have E1, epsilon 1, epsilon 2, R1, R2, R3. The only thing that I don't have are the currents, I1, I2, R3. That's 3 variables unknown. So I would need 3 equations. So if you just did 2 of the loop rules, like orange and blue, and then did 1 junction rule, that's enough to solve this formula because you only need 3 equations to solve for 3 unknowns. But having more just helps. It's backup. It just means that if you mess up, then you have more checks, more things to check and make sure you didn't mess up. All right. So that's Kirchhoff's loop rules. It's pretty much it. We are finished with our standard content for AP Physics 1. Congratulations. There's some advanced topics that we covered just in case, just for fun, and just in case. Those are, highly unlikely to be on the AP1 test, but they're good knowledge and good information to have with you when you go and move on to AP Physics C. From here on out, it's practice in combining topics, putting things together. Just because we're doing circuits doesn't mean it's different from mechanics, because you can use motors to lift objects, and you can do mechanical work using power and electricity, right? So our goal is to now combine all of the topics together. So let's go and use a motor to accelerate an object that will move in circular motion and then go through a roller coaster loop-de-loop or something. So let's go and combine everything that hits a block, that that swings a pendulum, that rings a bell, makes a sound. Sounds good. My final question will just be everything. Find the intensity of the sound after a bell is hit by a pendulum where a bullet crashes into the pendulum. Makes it swing upward based on the velocity of the bullet. Alright, so you have new mastering physics. Yeah, exactly. Or make your own. Ooh, sounds like a nice project. Starts crying in physics. Alright, so do mastering physics number 4. Of course, number 3 is like due at the end of this week. Number 4 is due next Wednesday. But I would get started. Remember, you don't want to start when it's due. You want to start when it's open, when I first give it to you. So do your mastering physics, and then download the second activity, Unit 8, and then look through it. We can get started on that tomorrow. Alright, that's it for today. Thank you for tuning in. I'll see you next time.